Hey everyone, welcome back. Last video we replaced a lot of the BGP WAN routing with EIGRP on top of the DMVPN overlays that we had established. So we had built tunnels from each branch location through the internet and the MPLS connections to form 4 total tunnels at each branch that went back to the data centers, and those 4 tunnels were spread across 2 WAN routers in the data center. So let's take a peek and just do some verification. I want to kind of dedicate this video to testing, some verification, maybe some failure situations, and we can also look at maybe manipulating some of the EIGRP metrics to favor one transit over the other. So I'm on site A, router 1. So if we showed the MVPN, we have the 4 tunnels that I was just referring to, okay? We should see the same thing on site B, router 1, which we do. And then the data centers, each router in the data center should have the corresponding tunnels as well. So it looks like we're all intact. Our tunnels are there, which that should mean, I'll just send this to all the sessions. Show IP EIGRP neighbors. So we should see on site A, router 1, we have the 4 tunnel peerings, and then we have the peerings to the switches that are below it, which is fine. Site B, we have the tunnels, and the data centers, we have the 4 tunnels as well as the links to the cores, and the same thing on WAN router 2, we have the 4 tunnels and the 2 peerings to the cores. So that all looks great. Let's check some of the routing tables now. So if we look at site A, we'll do show IP route EIGRP. So let's see what we have going on here. So we don't have a default route. Show IP route. Yeah, okay, we have that static route. That's right. Okay, so that we'll get into that. So let's do show IP route EIGRP. Let's focus on EIGRP for the moment. We have the 10 ones, which are the subnets at site A itself. So that's being learned from the switch, so that makes sense. We have some data center subnets, but I don't see branch B. So branch B should have the 10 twos. So we're not learning the 10 2 routes in site A. Let's check router or site B. Let's do show IP route EIGRP. So we have the data center subnets, but we don't have site A and site B. So it's the same story in site B. It doesn't look like they're exchanging routes. Or I should say exchanging, but it doesn't seem like they're learning routes from the data center. So is the data center learning the branch routes? So I'm on WAN router 1. I can see all of the subnets for site A, and I can see all of the subnets for site B. So that makes sense, right? We should see the same thing on router B, or excuse me, WAN router 2, I should say. Okay, so we see the routes from the branches, but it doesn't seem like the branch is learning the other branch's subnets. Now, this screams EIGRP split horizon to me. Let's double check something. So on WAN router 1, let's do a show run interface tunnel 0. So it would appear that we have the no IP split horizon set on our tunnel. Let's check tunnel 1. Okay, we do. I believe we had it set on the router 2 as well. Show run interface tunnel 0. We can see split horizons off for both tunnels. Okay. However, it doesn't seem like the routes are making their way through. So you guys know EIGRP split horizon basically says that it's a loop prevention mechanism, and it won't advertise a route out the same interface that it learned it in on. So in our case, since we're essentially kind of looking at a hub and spoke, logged me out, hang on. So if we look at the topology, right? Like let's hone in on site A, right? We have our connections going to the internet and the MPLS, which go to the data center, and they come in over that underlay, but they form the tunnel, and then it goes right, it's trying to go right back out that same interface to get to site B. So that's split horizon at its finest. But the question is, why does it not look like it's taking the command? I have a suspicion here, and honestly, this might be a really good learning curve or a good refresher. This is another good nugget that might make this video worthwhile in and itself. Let's do a show run section EIGRP. Okay, so on the WAN routers, we're running EIGRP in named mode. Okay, so that means router EIGRP, and then it has a name. All right, and then we dictate the address family, and then we put our network statements or whatever underneath of all that. So in named mode, so let me see if this is the problem, and then we'll chat about it. So I'm going to come under the routing process, and I'm going to type the question mark. So there's a command under the routing process that says AF interface. It says enter the address family interface configuration mode. So I'm going to type AF interface, and in our case, I want to look at the tunnels. So we can do tunnel 0. Okay, so this puts me in AF interface mode under the EIGRP process. Okay, I'm going to hit the question mark, and look at this. There's a keyword for split horizon. So I'm going to type split horizon, or I'm going to type no split horizon. So let's do show run section EIGRP. Okay, so check that out. So under the routing process now, right, there's an AF interface tunnel 0, and now I have no split horizon. So, and you saw what it did. It actually did a dual resync for the two neighbors over tunnel 0. So let's just take a peek. Before we do anything else, let's take a peek on A. So it did that resync on A, and it did that resync on B. Let's see if that changed the routing table. So I'm going to hit the up arrow, and wouldn't you know that, look at this. So for 35 seconds, since I typed that command in, all of a sudden we're now learning the other branch subnets. Okay? Well, in this case, it's the 10.2s. I highlighted the 10.1s, but it did the resync, so it re-injected those routes into the table. But the 10.2s, they weren't here a minute ago, right? They weren't here. They were missing. So now they're here. So that was the split horizon. So this is, if I'm telling you, if I were a test creator person, I would definitely put this on a test, because if you look at the show run, or the interface tunnels, right? When you look at the running config of the tunnels, you clearly saw that split horizon was not there. But that's not geared towards the named mode EIGRP. So when I come back down to named mode, you can see that there's another spot to put no split horizon. All right. So while we're in here, let's do the same thing for tunnel 1, because we want to make sure that we essentially advertise everything out of all interfaces. Show run section EIGRP. Okay, so now we have the same. I'm just going to copy this because I'm going to apply it to the second router as well. I'm going to lose my copy. I'm going to copy it one more time. So let's grab that, and then let's grab this one more time, and let's paste that on WAN router 2. Okay, so you can see it did a resync on all 4 neighbors, right? So now I would expect site A, show IP route EIGRP. Okay, so here's where it starts to get a little bit messier, right? So I had made mention of ECNP, or equal cost multipathing, in, I think it was the previous video. So that's what we're seeing here. So if we just focus in on the 10.2.0.0/24, that's being learned, or that's being advertised from site B to the data center over all 4 tunnels, okay? And then the data center is turning around and it's sending all 4 of those routes back to site A, or over to site A. So site A, for all intents and purposes, because all the metrics are exactly the same, it's going to try to do equal cost multipathing to site B using these 4 transits. Now, listen, if that's what you want to do, that's fine. In my experience, when you start to introduce all these routes, it starts to become goofy. You introduce out of order packets. There's all kinds of weird problems that you can start to kind of introduce. You think that you're doing yourself a favor by giving yourself all these redundant routes, but it's going to give you nothing more than a headache at some point in time. So this is what it looks like when you just kind of turn everything on and you advertise all the routes the way you would expect the routers to advertise them. So let's just chat about favoring one transit over another. So we know that we have MPLS and Internet in both branches. All right. Typically, your MPLS provider or service provider is going to offer you quality of service, some kind of a guarantee or an SLA on uptime and all that stuff, which is why you're going to pay more money for an MPLS circuit. So maybe it makes sense in your particular environment that you want to favor the MPLS because it's more, we'll say, dependable, okay? And the Internet is kind of a nice to have. Like when we had brought this into the picture like many videos ago, we were pretending it was like a cable modem or whatever. It gave us the direct internet access for our branch, but then we said, wouldn't it be nice to layer a tunnel on top of that to give us like some kind of a backup connection to the data center? So if we still use that same ideology or mindset, if you will, then we can put a delay on the internet side, which will make it less desirable, and that should mean that it would favor MPLS. So we'll take it one step at a time because I want to see what effects it has on the routing table. So if my logic would tell me that, in an environment like this, it's probably going to expand more than just like 2 branch sites, right? You're going to have many, many, many branch sites, sometimes hundreds, sometimes thousands, right? Like depending on how big the organization is. So if that's the case, maybe getting a delay on all the branch routers is a bit of a headache. So maybe you want to try to apply some kind of delay on the head ends because you're putting it in 2 spots versus 102 spots, right? Like that would be the argument. So let's try to do that. Let's see what happens. Let's go to WAN router 1 for starters. So we know that tunnel 1, I believe, was source interface gig 6, which is the MPLS, okay? So tunnel 1 is the MPLS, which we want to try to favor. Tunnel 0 is the internet, which we want to try to make less desirable. So let's go under tunnel 0. And let's just look at it. It should have the same exact config as tunnel 1 as far as bandwidth and delay. So it has bandwidth of 1000 and it has delay of 1000. If I scroll up a little bit, that's the same exact bandwidth and the same exact delay on the other tunnel, which is why it's doing ECNP, right? Because there's no difference between the two. So we're under interface tunnel 0. I'm going to introduce delay, and I'm going to do, you can see if I hit the question mark, you can put in anything between 1 and this number. So I'm going to do 5 nines. 1, 2, 3, 4, 5. Okay? So I'm going to introduce a delay of 5 nines. Let's do the same exact thing on WAN 02. So let's do delay 1, 2, 3, 4, 5. Okay? So we've just introduced a delay of 5 nines on the 2 head-end hub DMVPN routers. Let's come back over to router 1 and let's just hit the up arrow. And let's see if it did anything. So I still see 4 different ways to get to branch B, right? So it doesn't seem like anything changed. And you can see based on the timestamps of the table, nothing seems like it changed. Let's do a clear IP EIGRP neighbor. So that's going to force a resync of all our adjacencies, which will basically relearn the routes. So let's see if that does anything different. So we got the two neighbors, or excuse me, we should have the 4. Okay, so it doesn't look like it did anything, right? So the routes have been in there for 8 seconds and counting, but the point is they're all still there, okay? Let's go back to the WAN router, and let's do show IP route, EIGRP. Okay, so what it looks like that did, right, is that essentially stripped out one of the routes from the data center's perspective. Okay, so if we come over, let's split the screen here. So let's do show IP route EIGRP on WAN router 2 as well. So we can look at them side by side. So we can see that we only have the one route. So tunnel 1 is the only tunnel really being leveraged at the moment. Okay, so let's just do a comparison. I'm still under that tunnel. I'm going to do delay 1000. I'm going to essentially just put it back the way it was. All right, and then let's do clear IP EIGRP neighbor on both. So let's do, hit the up arrow a couple times. Okay, so you see the difference. So when the delays are the same, we get ECNP, and this is for the local router. Okay, so on the WAN, from the WAN router's perspective, going out to the branches, when the delays are the same, it does the ECNP, which we expect. When we introduce a delay on one tunnel, it strips that tunnel out or makes it less desirable going to the branches. However, it didn't have any effect on the branches going to the data center. So one thing you have to always remember is that, you know, when you start to get to that CCNA, CCNP level, right, you have to start checking the routing table from different devices' perspectives. So we think we're going to try to make it a quick and easy fix on the two head ends by introducing a delay, but it had no influence on the routes coming from the branches. So it's one of those things where, let me put the delay back on. So let's do delay 5 nines on both WAN routers. Delay 1, 2, 3, 4, 5. Okay. And then let's do the same thing on the branch side. So we said we want to favor the MPLS. Which is tunnel 1. So on tunnel 0, we're going to introduce the same delay. So delay, I don't know why I can't type delay, 1, 2, 3, 4, 5. So same thing on, let's go to the B router, because it'd be nice to see these side by side as well. So conf T, interface tunnel 0, delay 5 nines. All right. Now, I'm not going to clear EIGRP. Let's see if it figures itself out. So it looks like it figured it out on A. Let's give B a second. Okay, good. So it has to do the next update, and it looks like it now is favoring tunnel 1. Okay, out of both branch sites, as well as the, what we can say, the return path or the originating path from the data center as well. The point is, the internet tunnel is still there, okay, right? The tunnels are still there. And if we look at the EIGRP topology, so show IP EIGRP top, we can see that we still have the routes available at our disposal. They're just not in the routing table as the desired route as we speak, and that's because of the delay. So, you know, in my opinion, you're not losing anything, right? You're still going to be able to take advantage of the speed of the EIGRP convergence if there's an issue, right? And we're going to test that here in 1 second. But the point is, now we're kind of forcing our traffic, or we're favoring the MPLS because we know it has some guarantee, it has some quality of service. So it only makes sense to try to leverage that for, you know, the performance of our users. And then they can still, in theory, they can still go out the local internet using the cable modem, right? So let's do a couple failure scenarios here real quick. So let's go to, I guess we can just do it from a PC. It should be fine. I might have to reboot this thing. Let's see. Yeah, there's no IP on PC1. Let me just check. That should be VLAN 200, I believe. I'm almost positive, but let's just check. Let's change this host name back. Okay. So let's do show interface status. So link to PC1 is VLAN 200. So that's right. Let me drag this over. So that should be 10.1.1.0, right? So 10.1.1, and we'll make it 11/24. Gateway should have been .1. Okay. We should be able to ping the gateway. Okay, good. We should be able to ping. Let's just do a couple pings. Internet still works, which we'll get to that. And then let's go all the way down to server 1. So he's going to need an IP as well. Of course, I don't remember what VLAN you should be in. Show run interface E11. So that's VLAN 101. So that means he gets IP 10.101.11/24, and those gateways are 254 in the data center. So the question is, can I ping server 1 from PC1? Yes, I can. So connectivity is there. If I trace route to server 1, we can see that we favored tunnel 1. Okay, so that's awesome. That's what we want to see, right? So let's start a ping -C. Let's do 300. Hopefully I'll have enough time to demonstrate. So let's move him to the right. I'm not going to start the ping yet. So site A, router 1, we know that we went through the tunnel 1, right? So what we're going to do is we're going to down that tunnel after we start the ping, okay? So let's start the ping. I always do that. -C300, -C300. Okay. So the pings are going from the PC in site A to the server in data center 1. So let's go ahead and we're going to simulate an MPLS failure at site A. So that means interface tunnel 1, we're going to shut it down. Okay, so remember, we didn't tune EIGRP. We didn't try to go for the sub-second convergence. We haven't done any of that stuff. We're just playing with the default timers, whatever, right? You can see that we lost 2, 3, 4, 5, 6 pings. It immediately came back. So now if you do a trace route, and I should have figured out how to break these pings. The trace route should go over tunnel 0 now. Okay, so that's kind of the whole point behind this. If we do a show IP route, everything is now using tunnel 0. Okay, you can see it converged 52 seconds ago. So that's where all the connectivity reestablished, because it's now using the internet to go back to the data center. And the data center will figure that out as well, right? So do show IP route. So if I do show IP route for 10, what was it? 10.1.0, 2.0. Okay, so you can see it only has one route to get there now, and that's via tunnel 0. Okay, so if I bring that interface back up, all right, so if I no shut, all right, we see line protocol come up, the tunnel comes up, the PC didn't skip a beat, right? If I go back to the data center and I hit the up arrow, all right, let's see, we'll give it a second here. Do show IP route. Okay, there's our adjacencies. Okay, there's the adjacency. So now you can see I hit the up arrow and now it's tunnel 1. So a minute ago it was tunnel 0. All right, but since the service provider fixed their fiber cut or whatever the issue was, that circuit's now back up and you can see that it's favoring tunnel 1. So here we now see the loss of connectivity. It was 3 pings, so I spoke a little too soon. But that was even better than the actual failover event from the onset. So we only lost 3 pings. You know, a standard user, if they're browsing or working in some application or something, they're probably not going to feel that or notice it or make a big stink about it. 3 pings, that is. If they're on a video call or a voice call, something like that, they're probably going to feel that. You know, you might get, it might generate a call to the service desk or whatever. Earlier, when we lost 6 pings, there's a chance that can cause a Citrix session freeze, we'll say, like slowness. That's kind of the things you'll hear about in a situation like that. But for a network administrator, engineer, whatever, that's pretty good. I mean, you want to get fast convergence and you want to be able to be hands off. I would take that any day, you know. And again, we didn't tune anything. We can make that convergence way faster. Like you could get that down to 1 ping, no sweat. That's not a big deal with EIGRP. So you can see how easy it was to manipulate that traffic pattern with just introducing a simple delay statement. So let's do one more thing while we're together here, because I want to make sure everything's kind of intact, right? So show run include route. So we still have the quad 0 static route going out the internet for the DIA, direct internet access, right? And we have that track on there as well. I want to make sure that if the internet goes down, so we just failed the MPLS. I want to fail the internet and see kind of what effect that has on things as well. So if I'm pinging, I don't like the 888. I want to change that. I want to match what we did in Site B, to be honest. I want to ping. I want to do it with this address instead. Okay, so let's do this. Let's take the 8888 route out. So let's get rid of that. Do show run section SLA. I might have to stop this. No IP SLA 1. Just get rid of it. It's fine. We'll put it right back. We'll say we want to ICMP echo. We want to basically go to the service provider address. All right, and then we want to do show IP, show run section SLA. We got to start it, I believe. IP SLA schedule 1. Start time now, life forever. Do show IP SLA summary. Okay, good. So all I did was just repoint the destination of the SLA to the other side of the internet connection as opposed to 8888. So I'm going to ping from that same PC in Site A. I'm going to ping the internet. Now I'm going for the glory here. I don't know what's going to happen. I don't know if we've got the mechanisms in place to see if this works. And if we don't, maybe we stop, we'll come back and we'll troubleshoot it together next time. But let's see what happens. I'm going to start this ping. And I'm going to basically shut down Ethernet 0/1, okay? So let's start the ping, and then let's shut the interface. I believe, I think it's there. Like I said, I'm not sure. I can't remember. But we should essentially learn the default route back through the data center, or from the data center over EIGRP, and we should be able to get out that way. So if I check the routing table, okay, awesome. So we can see that we have a default route that we now have learned from EIGRP, okay? And by the way, this was fast because that route was sitting in the topology table waiting to be used, and the static route based on the track fell out of the table, right? So I know this is a little bit of a repeat, but when we show IP track, or do show track, we can see, why is that still up actually? Hold on. That's not right. Hold on. Do show IP SLA. Show run section SLA. $200,011. 200,011. Oh wow. Okay, I see what's going on. 200,011. Yeah. Okay. That's actually kind of funny. This is a good lesson too. So when you're playing with SLAs, I removed what we had for the 8888. So I had a route that forced it out of that link, right? So there's two ways you can accomplish this. You can either do it the way I originally had it, which is with the 8888. That's fine. Or you can do something different. So let's do this. Show run section SLA. Let's get rid of that SLA real quick. So let's do no IP SLA 1. Let's recreate it, but we're going to say I'm just thinking here. Do show run section track 1. IP route goes to there. Let's do no. Get rid of this. Let's do track 1 interface. What was the interface? It was Ethernet 0/1 line protocol. So this is another way to do it. All right, so instead of doing an SLA pinging something upstream or a couple hops away or whatever it was, we can track the line protocol on the interface itself. So when I did the failure scenario, I shut the interface, right? So I admined it down, which means that if we show track, right now we can see that interface 01, the track is down because it's admin down. So let's bring it back up just to bring it into the right state. So we can see the track went from down to up, right? So if we do show track, everything looks good. Do show IP route. We can see we have the static route in the table because it has the track 1's keyword attached to it. So let's down that interface one more time. Let's start our pings again. Well, let's trace route to 8880. So we're clearly going direct internet access out that hop, right? So let's do the pings. Let me do 50. So it's clearly going out DIA, it's pinging. I'm going to shut that interface and see what happens here. So we can see the track went down. Obviously the interface is down. We lost the tunnel. You know, all the repercussions of losing that interface do show IP route. The EIGRP route took over 21 seconds ago. It was almost instantaneous, right? So as soon as these 50 pings expire, we'll do a trace route and see where we're going. So this is good though. I wanted to just kind of retest this because the last time we tested this was through BGP. It was before we introduced the DMVPN. So if I trace route now, okay, good. So now if I trace route, we just essentially backhauled through the internet or through the data center out the internet. So what do we do? Let's summarize and then we'll probably end here. So let's go back to the topology. So we played with site A, and the first thing we did was we demonstrated the split horizon and the fact that it was it's in multiple places in the config, right? So once we did split horizon, we fixed that. We were able to learn the routes from the other branch sites. So that was preventing the WAN routers from re-advertising the route back to the opposite site because it came in on the interface it was learned on. So we fixed that issue. Then we had 4 possible routes to reach those destinations. So we introduced a delay to favor one tunnel over the other. We saw that it had no bearing on the redundancy aspect of things. It just cut down the routes from 4 to 2. So then we failed the MPLS. So we simulated a failure of the MPLS at site B. It automatically failed over to the internet tunnel back to the data center with loss of 6 pings initially, 3 pings on the reconvergence. So that wasn't the end of the world. Then we double checked our SLA on our track for the direct internet access, and we downed the direct internet access, and we can see that the routing still worked back through the data center and out, and the convergence time there was almost negligible. So that's quite a bit to unpack, but that's a product of all the hard work, right? We've tested all the scenarios now. We know we have full connectivity across the environment. All of our mechanisms are in place, and we can sleep better at night knowing that all of our hard work has paid off and that we have redundancy, and we should get less phone calls and less, stressful moments to troubleshoot why the network's down. So I'll stop there. I hope you guys enjoyed it, and I will see you on the next one.